talk. And there we go. Thanks for inviting me to give this talk, and everyone for coming. It's an honor to speak for such a distinguished audience. So in today's talk, I'm going to be talking about some recent results, which I've put on the archive, where I compute the wavefront set, the spherical Arthur representations. And so without further ado, I'll get right into it with motivations for why one might care about these things. So the motivation comes from automorphic representations. And the setting is we consider a reductive group defined and split over some number field F. And it's known that if you have some automorphic representation, so a sub-representation of the space, you can decompose it as a restricted tensor product. And the restrictions that all but finitely, many of these representations, so this is a tensor product over all places for the number field, all but finitely, many of them are spherical. And there are many spherical representations for a p-adic group, but conjecturally there's a very specific small class of spherical representations which occur in this way, and they have a description, a conjectural nice description in terms of Arthur parameters. So without sort of delving too much into the specifics, since this is motivation, here G check is the dual group, so we're going to assume we're working in the split case. Then conjecturally, the Arthur parameters which these spherical representations occur in are trivial on the Vedelin group, and within the packet parametrized by that parameter, they should correspond to the trivial representation of the component group of the centralizer of the image. And since Arthur parameters are defined with the conjugacy by the Jacobs and Morozov theorem, there's a bijection between homomorphisms up to conjugacy and nilpotent orbits of the Lie algebra. And so we have a description of the spherical representations which occur in this fashion in terms of nilpotent orbits. And we call the spherical Arthur parameter, which corresponds to the orbit O, spherical Arthur representation with parameter O. So these are why these representations are important. The reasons why we care about the wavefront set, again, without going into too much detail, there's a notion of a wavefront set which we can attach to an automorphic representation, defined in terms of certain degenerate Fourier-Whittaker coefficients. And crucially, there's also a notion for each of the local factors of a wavefront set, and sort of the reason why we care about the wavefront sets of the local factors is we have this inequality. So the wavefront set of the automorphic representation should be a lower bound for the wavefront set for all the local factors that occur. And I'm putting quotation marks here because wavefront sets are collections of nilpotent orbits, and on the left-hand side and the right-hand side, they're defined over different base fields. So a priori, we can't necessarily compare these things, but if you have a reductive group over an algebraically closed field, the nilpotent orbits, they have the same structure as if you were defined over the complex numbers, and sort of by that transport of structure, there's a comparison that can be made in that fashion. And what are some of the consequences of this inequality? So if the wavefront set is large, it imposes tight structural restrictions on the local factors. And conversely, if you know any of the local factors, and since most of them are spherical, these results that are obtained for spherical Arthur representations allows you to upper bound the wavefront set for the automorphic representation. So that's the motivation. So I'll be talking about the p-adic case. So I will give a proper definition for the wavefront set in that setting. But before I do, I'd like to fix some notation. So there'll be a lot of fields at play in this talk, and it will help to fix it, the notation at the beginning. So K will be our p-adic field. So it's some finite extension of the p-adic numbers. These are the local factors that occur when we're looking at number fields, the non-Archimedean ones. We're going to fix an algebraic closure K bar of our base field K. And inside of that, we're going to consider the maximal unramified extension. capital K. And there's an equivalence between finite extensions of the residue field and unramified extensions of K. And so naturally the maximal unramified extension has a residue field, which is an algebraic closure for the base field for F. So these are the 5 fields at play, and these are the ring of integers for these respective fields here. And in general, we'll use TypeScript notation to refer to things in this first column. So either related to the p-adic field or its residue field, and we'll use uppercase and lowercase letters to sort of distinguish if you're up here or down here. We'll also use uppercase and lowercase for the Lie group and the Lie algebra. And for the unramified extension, we'll use calligraphic fonts, and for algebraically closed fields or schematic objects, we'll use boldface fonts. In this case, there were 2 options, either calligraphic or boldface, and we've just gone with boldface fonts. And to fix some terminology, we'll refer to nilpotent orbits over the p-adic field as p-adic orbits, nilpotent orbits over the maximal unramified extension as unramified orbits, and orbits over the algebraic closure as geometric orbits. Similarly here, we'll call these geometric orbits. Although in text we might write K-rational or something like this. So I'll come back to this slide throughout the talk in case it's a bit much to take in at this moment. But without further ado, I'll introduce what the wavefront set is for the p-adic group. So in this case, we're going to fix our reductive group. For the purposes of this talk, you can always assume it's split, and it's going to be defined over K. And we're going to let G and little g define the K points of the group in its Lie algebra. So the wavefront set is an invariant you can attach to an irreducible admissible representation of G, and it's defined in terms of the Harish-Chandra Howe local character expansion. So to unpack what those words mean, if you're not familiar with them, so the character part of that is the character distribution, which you can attach to pi, and it's the exact analog of the character, but for a p-adic group, but where the character is sort of extended linearly across the group algebra. But in the p-adic case, you need to replace summation with integration, but for all intents and purposes, it sort of serves the same function for us. And the local character expansion relates distributions on the group to distributions on the Lie algebra. To have such a comparison, we need an exponential function. And due to convergence issues, this could only hold locally. So the neighborhoods of 0 and 1, for which we have a bijective exponential function, which we can use to compare these things. And then the local character expansion states that, so for every p-adic orbit, which I've denoted by O sub k to indicate the base field and 0 to indicate nilpotent, we can always attach, we can find coefficients for each one of them, depending on the representation, such that for functions supported sufficiently close to the identity, we have this equality of distributions. So this is a linear combination of Fourier transforms and nilpotent orbital integrals. So it's not too important exactly what form this takes for this talk, but sort of roughly speaking, for every nilpotent orbit, you can attach a measure, and then you obtain a distribution on functions on the Lie algebra by restricting to the nilpotent orbit and integrating. And then the Fourier transform of the nilpotent orbital integral is the usual thing where you apply the distribution to the Fourier transform of the thing inside. So this is incredibly powerful. These coefficients are incredibly powerful information which encode a lot about the representation, and for our case, we use it to define the wavefront set. So there's natural partial ordering on the nilpotent orbits, the p-adic nilpotent orbits, given by the closure ordering. So this is not using the Zariski topology. The p-adic field comes with its own topology, which endows a topology on the p-adic group and its Lie algebra. And it's with respect to this topology that we obtain the partial order on the set of nilpotent orbits. The wavefront set, specifically the p-adic wavefront set, is then defined as among all the nilpotent orbits which occur when non-zero coefficient in this local character expansion, they're the maximal ones with respect to this partial order. There have been several techniques developed over the years to compute this invariant. In '87, when Glenn and Moss-Paget develop techniques using degenerate Whittaker models, which is sort of what connects it with the automorphic forms picture. And in 97, Barbash and Moy developed the techniques using so-called lifted generalized Gelfand-Gruyev representations. And while this is an incredibly powerful invariant you can attach to a p-adic group, the p-adic wavefront set, as I've stated it now, is incredibly difficult to compute. And the most comprehensive result I know in that direction is by Monglen and Vosperger, again in the same paper, where they compute it for GLN and subquotients of the regular principal series for split classical groups. And the reason why there maybe hasn't been more results in that direction is because, motivated by the real case where you also have wavefront sets, it's expected that all the p-adic orbits lie in the same geometric orbit. And so sort of a first approximation to solving this problem is to determine what is the maximal geometric orbit in which all of these, in which the wavefront set lies, which all the, I'll explain now. So in general, we have, for a p-adic orbit, it lies in some uniquely determined geometric orbit, which we denote k bar of O. And again, we have a partial ordering on the geometric orbits, but this time the closure ordering with respect to Zariski topology. And then the algebraic wavefront set are the maximal geometric nilpotent orbits, which occur in the local character expansion. So this is where sort of most recent progress has been made. And notably in 2018 and 2020, whilst Bruhat used slightly different methods than before, a similar vein, but still different from this talk, to compute it for the anti-tempered and tempered representations of inner forms of SO2m plus 1. And it's a real tour de force and sort of combinatorics of generalized Springer correspondence, very impressive results. So the thesis, now I mentioned the methods by Barbash and Moy, and they were developed in 97, but sort of promptly forgotten by the research community. And my sort of thesis problem when I set out on this was to see if we could get any mileage out of the techniques developed there. And so I'm going to briefly outline sort of the ideas from that paper. But sort of central to all of that, we do need the Bruhat-Tits building. And so I'm going to give us a brief primer on what that is, in case you haven't seen this before. So the Bruhat-Tits building, for the purpose of this talk, we're going to just, I've written poly, but you can just assume simplicial. So I'm going to say it's a simplicial complex on which G acts by simplicial morphisms. So polysimplicial just means a product of simplices, but we're going to work with quasi-simple groups. So simplicial is fine for our purposes. And it's some notion of a generalization of the flag variety, but it's a combinatorial object which encodes a lot of information about the p-adic group G. And more or less, it consists of gluing together apartments. So an apartment is the co-root lattice for a particular choice of torus. Again, we're assuming split here. So some particular choice of maximal torus, maximal torus, which is, and you tensor the co-root lattice with R. So you get an apartment for each such split maximal torus. And the Bruhat-Tits building is obtained by sort of gluing them together. And so I've drawn here the apartment for SP4, and obviously this vector space isn't enough to make it a simplicial morphism. And the way it gets its simplicial structure is by considering integral vanishing of roots on this space. So this is the vanishing set of alpha 2, the root alpha 2. This is the vanishing of alpha 2 minus 1. So alpha 2 takes value 1 here. I don't know if you can see my mouse when I sort of indicate that things. And this hyperplane here is alpha 2 is equal to 2, etc. And then the simplicial structure are these alcoves. They're called alcoves. So what do we need to know about the Bruhat-Tits building for our purposes? Well, it acts by simplicial morphisms, so we can choose a facet of our building C, and it has some stabilizer defined over the integral points of spec of O, and the reductive quotient of this stabilizer is then a reductive group defined over F. And we can fit things into this short exact sequence. So we have a map from the stabilizer to the reductive quotient. These are the F points of it. And we have some kernel, which is some pro-unipotent radical UC. Now we aren't usually interested in the full stabilizer in our context. And so the thing we're interested in is the pre-image of the identity component of this reductive quotient. And we denote it by P sub C, and it's the parahoric subgroup of G. And it plays sort of the analog of a parabolic subgroup in the p-adic setting. And just to give a couple of examples of what these things look like. So again, in SP4, if we take C0 to be the vertex corresponding to the origin, then the parahoric subgroup is just the integral points of SP4, and the reductive quotient is SP4 defined over FP. And the map from here to here is just reduction mod P. And the pro-unipotent radical are matrices of this form intersected with SP4. So I've omitted the intersection, but that will always be assumed when I write a matrix of this form. And if we take a slightly less trivial example, if we take C1 to be this vertex here, the parahoric subgroup attached to that vertex, it looks slightly different. It looks like this, but crucially, the reductive quotient is sp2 cross sp2. So we have these two copies in here which don't interact. And crucially, if you look at the hyperplanes going through this vertex C1, they're exactly 2, and the root system through it is of type A1 cross A1, which is exactly the root system of the reductive quotient. And this is no coincidence, and this is sort of the only thing you really need to know about the Bruhat-Tits building for this talk. So if we fix some fundamental alcove of our apartment, and by fundamental alcove, we just mean the chamber cut out by the extended simple roots. So we fix some root system, then this is the vanishing of alpha 2, this is the vanishing of alpha 1, and alpha naught tilde here is 1 minus the highest root of the root system. And that fits into the extended Euclid diagram as the affine node. So this is the highest root equals to 1 hyperplane. And I've labeled each of the facets of this chamber by the roots which vanish, the extended simple roots which vanish at these facets. And the way to determine the structure of the reductive group, at least the root system, is you look at the extended Dinka diagram. So if we take this vertex here again, C1, we have alpha naught tilde and alpha 2. And the Dinkin diagram with only these two vertices are exactly two like empty points. And so indeed, the reductive quotient has root system of type A1 and A1. Similarly, if we take this vertex here, that's alpha 1 and alpha 2, that has root system of type C2. And so we get a reductive quotient of SP4. And these are all defined over FP. And lastly, I'll give this vertex here, alpha naught and alpha 1. Again, this is a root system of type C2. So you get SP4 here as well. Now, what you don't get is the isogeny of the reductive quotient, but root system is all we need to know for the purposes of nilpotent orbits. So this is sufficient for us. So why do we care about the Bruhat-Tits building in our applications? Well, one of the main things we need for Barbash and Moy's methods is to be able to lift nilpotent orbits. So remember, we have our p-adic field and we have a reductive field. And what you can do is you can lift a nilpotent orbit defined in the reductive quotient to a p-adic orbit. So I'm going to explain quickly how that happens. So if you have some facet C of the building, and X is a nilpotent element of the reductive quotient, we can look at the Lie algebras of the parahoric subgroup and the reductive quotient, and we can look at the pre-image of X in this map, and that's some coset of UC in PC. And crucially, the collection of p-adic orbits which intersect this coset is non-empty. And if you look at that partially ordered set, there's a unique minimal element in that set. And we denote that by OCX. And this is so-called lift of the nilpotent element X to a p-adic orbit. And just to give a couple of examples of what that looks like, I'll just do this briefly. So again, in C0, the reductive quotient is SP4 FP. If we take this nilpotent element with partition type 2, 2, then the lift is just essentially the same thing, but these ones are in the field QP rather than FP. So it's the orbit, nilpotent orbit of this. If we take our facet to be C1, this other vertex, our reductive quotient was sp2 equals sp2. So we take the regular orbit here. Then the lift, it looks the same. It lies in the same geometric orbit, but we have this pi1 inverse in the lift in this case. And as a p-adic orbit, it's distinct from the previous one. So we obtain two different p-adic orbits in this manner. Continuing from the previous slide, which I'd shown, in particular, if we have x and x prime lying in the same nilpotent orbit of the reductive quotient, they lift to the same p-adic orbit. So what that does is it gives us a map from I sub k. And I sub k is the set of all pairs C, O, where C is the facet and O is a nilpotent orbit of the reductive quotient. And it gives us a map to the p-adic orbits. We call this map O as well, and it's surjective, crucially, and it can be used and has been used by Barbash and Moy and De Backer to classify all of the p-adic nilpotent orbits. It's a very powerful concept. So that's one reason why we need it. There's another reason why we need it for Barbash and Moy's techniques. And the other reason is we can attach certain finite representations. So if we pick a pair C, O, we can construct a representation of the reductive quotient called gamma sub O, called the generalized Gelfand-Gruyer representation attached to O. So this is a general construction you can do. If you have a finite group of Lie type in a nilpotent orbit, you can construct a representation of the finite group. And so we use it in the special case where we have the reductive quotient of some facet C. And if you take the character of this representation and pull it back along the projection map and extend it by 0 outside of the parahoric subgroup, what we get is a compactly supported smooth function on the group G. And the reason why this is useful is because for each facet C, we also have a finite dimensional representation of the reductive quotient obtained by taking the space of fixed vectors with respect to the pro-unipotent radical. So the pro-unipotent radical is normal inside of the parahoric subgroup. So this representation descends to a representation of the finite, of the reductive quotient. And sort of the key result that we need is that if you take the character distribution and you evaluate this function that I've described, what you get is the inner product between the smooth dual of V and then the UC fixed vectors of that, together with the generalized Gelfand-Gruyer representation. And why is this useful? Well, so Barbash and Moy had two techniques for calculating the wavefront set. They had one which involved understanding the whole local character expansion, but they had this other idea where they wanted to understand the wavefront set in terms of wavefront sets of these representations that I've just described, these VUCs. And there's a notion of wavefront sets for finite groups of Lie type as well, which they were hoping to relate it to. And the definition in the finite case is the wavefront set of a representation of some reductive group defined over F is the unique maximal geometric orbit with the property that there is some F rational orbit lying in that geometric orbit, which pairs non-zeroly with the representation. So that's the wavefront set for this space here. But on the nose, and maybe why the idea didn't necessarily gain traction immediately, is that because there is no geometric or topological structure on the finite group of Lie type. Sort of Zariski topology just gives you a discrete topology, and so there's no interesting closure relations on F rational nilpotent orbits. And so as a result, it's very difficult to compare the lifts of those nilpotent orbits to p-adic orbits. So even though you have this property of the geometric orbits, it doesn't necessarily tell you relations between the p-adic orbits, so it gives you very weak relations. And the other reason why it's difficult to use this idea is because while determining the geometric orbit of the wavefront set in the finite case is easy to describe. I should put easy in quotation marks, but it has a nice description in terms of Lustig's geometric classification of irreducible representations of finite groups of the type. The F rational orbits inside of that don't have a easy description. But somehow the way to remedy the situation is actually to forget about the F rational nilpotent orbit and just look at the geometric one. So somehow we're interested in the algebraic wavefront set, and so we can get away with this. And returning back to this picture here, I said you could lift nilpotent orbits from the reductive quotient here to get p-adic orbits. The analogous picture holds for geometric orbits of the reductive quotient. What you get is you lift and you get an unramified orbit. So this is why unramified orbits come into the picture. They're sort of the natural thing to consider if you want to do use the geometry of the reductive quotients. So let me briefly describe how this works for k-rational orbits and geometric orbits. So the exact same procedure works. We can consider pairs C, O, where C is a facet of the building and O is a nilpotent orbit of the reductive quotient, a geometric one in this case. And once again, we have a surjective mapping, so we can obtain every unramified orbit in this manner. Sort of one of the crucial properties of this lifting map in this case is that it preserves the partially ordered structure on the reductive quotient. So we have a partial order on the geometric orbits of the reductive quotient just given by the Zariski topology, which is now meaningful over an algebraically closed field. And if you have two nilpotent orbits in the same reductive quotient, which are related, then the lifts are also going to be related. So we can now actually use this maximality condition constructively somehow. And this then motivates the definition of a different kind of unramified wavefront set. So one that hasn't really been considered in the literature till now. And it's the maximal unramified nilpotent orbits which occur in the local character expansion. And sort of the sort of realizing this idea of Barbash and Moy, then we can define so-called local wavefront set operators. For every facet C, we can define the lift of the wavefront set of the representation of the reductive quotient. So I've only defined it for reducible representations. This could be reducible, but the wavefront set of a reducible representation is just the maximal nilpotent orbits of the wavefront sets of all the irreducible constituents. So we can define these local wavefront set operators, which are just the lift of that wavefront set. And then sort of realizing this idea that they had, we get exactly what you would hope to do, but we just need to pass to the unramified orbits. We get that the unramified wavefront set is just the maximum of all the local wavefront set operators, where C ranges over, we can restrict this maximum so that C ranges over the facets of a fixed chamber. So this is a finite maximum to calculate. Okay, so this sort of boils the problem down to simpler problem. We need to understand what are these local wavefront set operators first of all. And sort of for a large class of representations, which includes the representations we're interested in, so the spherical Arthur representations, there's a Q goes to 1 operation, which we can apply to these finite representations of the reductive quotients. I'll call them finite representations, even though that's perhaps a bad use of terminology. And what this Q goes to 1 operation does is that it gives us a representation of the Val group of the reductive quotient. So WC is the Val group of the reductive quotient. And essentially it goes by sort of obtaining a Hecke algebra representation. Since it's a finite Hecke algebra, it's a Hecke algebra of a finite group of the type, we can deform it using this isomorphism by Lustig. And so we get a representation of WC. And then it reduces to understanding sort of an equivalent notion of what a wavefront set is, but for representation of the Val group. And so it's not too important exactly what this is, But for those of you that are familiar with families of representations of violent groups in terms of cells and sort of the Springer correspondence, it is the Springer support or the unique special representation in the same family of E tensor with sign. Again, it's not too important to know what exactly this is, but crucially, we can use this nilpotent orbit, this geometric orbit, to compute what the wavefront set is for this finite representation. And then sort of putting it all together then, to compute the wavefront set, you just consider all the irreducible constituents of the Q goes to 1 of this finite representation and compute O of E. So from a theoretical perspective, that is all we really need for computing the local wavefront set operators. Obviously, we need to know what the structure of these representations are. Sort of from a general theory perspective, that gives us sufficiently nice description to make this problem tractable. So there are two. Let me see how I move it on. So there are two outstanding issues. So if I just go back here, I've told you how we can compute these local wavefront set operators, but we also need to be able to compute this maximum. And at the end of the day, we're interested in the algebraic wavefront set. So there are two outstanding issues. What are the unramified orbits? So I've given you a description of it in terms of these lifts, but ideally we'd have a description of it which allows us to easily be able to tell what geometric orbit it lies in. And this description that I've given earlier does not address this issue. So it's not obvious immediately how to figure out what the geometric orbit is. And the second outstanding issue is, what are the closure relations on the unramified orbits? So if we want to compute this maximum, we need to be able to tell when they're related somehow. The answer to this first question and this associated question that comes to it is actually a resounding yes, and it's remarkable how well this is, like how nicely this is answered. This is one of the earlier, this was the first result I had from my PhD, and it goes as follows. So if you have a split reductive group, if you take the split reductive group defined over the complex numbers now, but with the same root datum as G, we can get a parametrization of the unramified orbits in terms of data on G sub C. So if we let ds denote the set of all pairs O, C, where O is a nilpotent orbit and C is a conjugacy class of this so-called G equivariant fundamental group of O. And what this fundamental group is you can think of it as the component group of the stabilizer of a nilpotent element in this orbit, and that is well defined up to conjugacy. And the result that we get is that there's a canonical bijection between these pairs defined on the complex reductive group and the unramified orbits. And in particular, it's compatible with taking geometric orbits. So for these pairs O, C, we can always project onto the first component to get a geometric an orbit over C. And as I've described earlier in the talk, there's this, if you have a split reductive group defined over an algebraically closed field, the partially ordered set of nilpotent orbits is always equivalent with if the characteristic is sufficiently large, is always equivalent as a partially ordered set to the nilpotent orbits over the complex reductive group. And
sorry, can I answer a question?
Yep.
Sorry, I didn't catch. What's the map P1?
So P1 here is projection onto the first factor. So DS stands for dual Springer parameters, but I've been told that that is a little bit confusing because there's also Springer parameters on the dual side. But by the duality here, I just mean conjugacy classes instead of irreducible representations. But the dual Springer parameter consists of all pairs of O and C, and O here is an element of this set. So we can always project onto the first factor to get an element here.
Okay. Yeah. Okay. Thanks.
And so that under this identification, determining the geometric orbit is a trivial thing to do. You simply read off the first component in this pair. And so this completely answers the first question and the concern regarding characterization. And it actually gives us a lot of new structure all of a sudden, because the second question, the question about the partially ordered set, actually I don't know an answer to. So in general, the partially ordered set of unramified orbits is not an easy thing to understand. There's a sort of a lot going on, but what we get gifted from this identification is a way to work around it, actually. So we can sort of circumvent that issue, and I'll describe it now. And like I said, the key observation is that this identification endows the unramified wavefront sets, the set of them, with suddenly a whole lot of new structure, because this set here is the unramified wavefront sets, not a particularly well studied object in theory of p-adic representations, or in general, as far as I'm aware of. But this set of dual Springer parameters is very well studied. And the first piece of additional structure that we obtain from this canonical bijection is Sommers's duality map. So Sommers was a student of Listic, and he defined this remarkable duality map from these dual Springer parameters to nilpotent orbits of the complex dual group. So the complex dual group is just the reductive group defined over C with dual root datum. So you swap to the co-root and root lattice and character lattice and co-character lattice. And so this map defined by Sommers is a generalization, if you're familiar with it, of Barbash-Vogin and Listic-Spaltenstein duality. So Listic-Spaltenstein duality is sort of a generalization of the notion of taking the transpose of partitions. So in reductive groups of type A, the nilpotent orbits, if you're over C, are parametrized by partitions of n, say GLN, and the Listic-Spaltenstein dual is then the transpose, and it generalizes this notion to all reductive groups, and the Sommers map is a further generalization of that, even more so. So we get this new duality map on the dual Springer parameters, and the remarkable thing that this allows us to do is it allows us to get a new preorder on the unramified wavefront set. So Okada did this in 2003. He used Sommers's duality map to define a preorder on the dual Springer parameters, and the most natural description of it is it's the finest preorder, which simultaneously makes the Sommers duality map order reversing and the projection map order preserving. So explicitly, we say a pair is less than or equal than this pair if the Sommers map flips the order and the projection preserves the order. But crucially, this canonical isomorphism is not an isomorphism of preorders. So we have closure relations on this side, and we have a Okada's preorder on this side, and they're not the same thing, and they can't possibly be the same thing. So this closure ordering on the right-hand side is a partial order, while the preorder on the left-hand side, there are non-trivial equivalence classes, in fact, most of the time. Well, maybe not most of the time, but very frequently. What I can say is conjecturally, the map from the right to the left is an order preserving map. So conjecturally, if you have a relation between unramified orbits, that should give you a relation in the Okada ordering. But this relies on a conjecture in the paper, which is yet unproved, but it is not necessary for the results. But yes, but somehow this preorder is much easier to understand than the partial order on the unramified orbits. Indeed, Okada extensively studied this in his 2003 paper, and he came up with some beautiful descriptions of it. And in particular, the equivalence classes. So again, a preorder is not necessarily anti-symmetric. So if x is less than or equal to y, and y is less than or equal to x, we don't necessarily have equality in a preorder, but it defines maybe a notion of quasi-equivalence, if you will. And the quasi-equivalence classes, which I just call equivalence classes, they're very well understood for this preorder. So if we let ds bar, if we let it denote the set of all pairs O, C, where O is again a nilpotent geometric orbit, but C is now a conjugacy class and lists its canonical quotient. So if you've run into the canonical quotient before, this is something that's usually defined for adjoint groups. But in Summers's paper, where he introduced the Summers duality map, he extended the notion of Lustig's canonical quotient to arbitrary isogenies. And so we can define Lustig's canonical quotient in general, and it is indeed a quotient of this group, as the name suggests. So there's a natural map from pi1g of O to the canonical quotient. And what that does is it gives us this essentially very natural map. So this map sends a pair O, C to O, C bar, if you will, where C bar is the conjugacy class and the canonical quotient, which is the image of C under the quotient map, essentially. And then after, if we compose that with the canonical bijection identifying these two sets, then the equivalence classes are exactly the fiber of this map. So we have a very explicit description of equivalence classes as a result. Another amazing feature of Okada's work is that he also introduces an even further refinement of Summers's duality map. So we can also consider ds bar for G check. And what Okada did is he defined duality maps going both ways between these two sets, which extend Summers's duality map in the sense that the following diagram commutes. So you can recover Summers's duality map by first applying this quotienting map that I described in the previous slide, applying Okada's duality map, and then just simply projecting on the first factor. So somehow these duality maps are even more sensitive than both Barbach-Vogan's, Lustig and Spaltenstein's, and Summers' duality. They contain even more information. And the very reason why this is relevant for our talk is that it provides an incredibly convenient bridge. So eventually what we want to do is we want to compute the local wavefront sets. And this will be done by looking at equivariant perverse sheaves on the nilpotent cone of the dual group. And what this Okada's map will do is it will allow us to transfer information we obtain from these equivariant perverse sheaves and obtain information about equivalence classes of unramified orbits on the left-hand side. So it will play an essential role in our calculations. So we now have completely new pre-order structure on the unramified wavefront set. And so we do the natural thing and we can use it to define modification of the unramified wavefront set from before. And we call this the canonical unramified wavefront set. So if the conjecture that I mentioned earlier, its definition is entirely analogous to the other wavefront sets. It's the maximal unramified orbits in the local character expansion, but we're now with maximality respect to this new preorder. And maximality with respect to a preorder just means x is maximal if whenever it's less than y, y is less than x as well. In general, there is a concrete definition which I give in my paper, but it uses some notation that I haven't introduced in this talk. And somehow this is morally what you need to know about it. And crucially for our applications, what really makes this work is that we can calculate the algebraic wavefront set directly from this canonical unramified wavefront set. So if you just consider the geometric orbits which the wavefront sets lie in, that will immediately tell you what the algebraic one is. And this result that I stated earlier about calculating the unramified wavefront set locally holds exactly on the nose as before as well. So these are theorems, and they don't depend on this conjecture that I've mentioned. You can just genuinely compute the canonical unramified wavefront set as before, but where you replace the partial order with this pre-order by a car. So it is exactly what we need for our purposes. So that sets up the general theory and the machinery that we need to compute the algebraic wavefront set for spherical Arthur representations. So let's do some specific computations for that. So we're going to let pi comma v. So how am I doing for time? So we're going to let pi comma v denote the spherical Arthur representation with parameter O check. And we're going to let n just denote some nilpotent element of that parameter. And we're going to let dot, so the gradient, denote the projection map from the extended Val group to the Val group. So the extended Val group acts on an apartment by translation of the code character lattice. And we can always just take the gradient of that affine transformation. And that's this projection map here. And we're going to fix, as before, an apartment and a fundamental chamber. So that's the chamber cut out by some system of affine simple roots. And the key result we need for spherical Arthur representations is that the structure of these finite representations are just the restriction of the total cohomology fiber of the space of Borel's containing the nilpotent and taking the trivial isotypical component of the component group action on this total cohomology. And then this is something which has a W action by general Springer theory. And the structure of, if you take a particular facet of your chamber, that corresponds to sort of choosing a subset of your extended simple root, then the WC, the Val group of the reductive quotient structure is just, it's very nice in the spherical Arthur representation. It's just genuine restriction to WC as a subgroup of W by taking gradients. And crucially, we can define these sheaves. So for an irreducible representation of the Val group of the reductive quotient, we can define these perverse sheaves. And it's not too important exactly this expression. The key thing is that this is the multiplicity sheaf for the representation E in this representation of this finite representation. So this is what this next point states. So if you take Q goes to 1 of this finite representation, then the multiplicity of E is equal to the multiplicity of the trivial local system of this perverse sheaf restricted to this nilpotent orbit O. And what I include here is a bound of this number. So, and the bound is the dimension of this total cohomology space, of this perverse sheaf. But the reason why I include this bound is I want to say, unless this O check is contained in the support of this multiplicity sheaf, E will not occur, will not contribute to this representation here. So
could I just interrupt a bit? Can I clarify what is the meaning of I.4? I mean, the one with equation 26. Is it the structure of this is this? So, but this expression in 26 have no V doesn't intervene. So I was wondering what is meant by that.
Yeah, sorry. So this should be V. First of all, Q goes to 1 here. So V is it's a particular representation. Yeah. This is the parameter N.
Oh, okay. V is a specific representation. Okay.
Exactly. Yeah. It's the Arthur representation with this parameter, and you can calculate. Yeah.
And in 27, what is the subs? The direct sum over, because you have a W.
Yes.
V and then.
Yeah. So if you take the reductive group over C and the reductive and the dual group, the Val groups are isomorphic, but somehow the isomorphism it's by identifying the root with the co-root, the reflection in the co-root. So we can identify, so WC, the Val group of the reductive quotient is naturally a subgroup here.
I think I got. Thanks.
Yeah, brilliant. No problem. So let's consider again our representation E. So again, we're looking at the multiplicity of E in this expression here, and it's given by this quantity. So if it were to contribute to the wavefront set, then the lifted unramified orbit would be, okay, tautologically it would be the lifted unramified orbit, and let's denote the lifted unramified orbit by O. So the crucial piece of analysis of this perverse sheaf that you need to do is that, remarkably, the support of this perverse sheaf is exactly contained in the closure of the Summers map applied to the lift of that, the Summers map applied to this unramified orbit. And this provides us exactly one of the directions we need to calculate the algebraic wavefront set. So if this holds, if O of E contributes to the local wavefront set operator at C, we must have that O check is less than or equal to the Summers map applied to the unramified orbit. And recall we have the following diagram. So we have this canonical identification, which I've described, and we have this canonical identification, and this diagram commutes. But this diagram does not commute. So this is the Barbash-Vogin duality that I mentioned, which is sort of a special case of Summers duality. This diagram doesn't commute, in fact, but what you do have is that P1 is always smaller than or equal to going around this direction here. So identifying these two things with each other, what that means on the level of unramified orbits is that the geometric orbit of O is always less than or equal to the Barbash-Vogin or the Summers duality of O. So what does that mean in our context? Well, if we apply Barbash-Vogin duality to this expression here, we get this inequality. So if OE contributes to the wavefront set, this inequality must always hold. But we also have, by point 4, that this inequality always holds. So what we get is we get an upper bound for any unramified orbit in the unramified wavefront set in terms of the Barbash-Vogin dual of O check, the parameter of the spherical Arthur representation. I realized that I forgot to mention this, but I've denoted this map ds. But when I identify these two objects, I also call the composition ds. And similarly for the Barbash-Vogin dual. So when I identify these two objects, I call the resulting composition also dBV, in case there's any confusion about the codomain of any of these maps. But one can actually say more. So one needs to be a bit careful, and one needs to go into the definition of Akar's preorder. But what this also actually tells you is you get a lot more mileage out of it. You get that, so this is again the pre-image in this ds bar that I described earlier. You can actually say that that is contained inside of the Akar dual of O check, 1. So this analysis that I've just given gives us, first of all, an inequality here. So we obtain this inequality and we obtain this inequality, an inequality here. And for the purposes of this talk, I won't be able to go into the more careful analysis that's needed to give the reverse inequalities. But just some consideration of the local systems which occur of certain restrictions of these perverse sheaves gives you these results. And so sort of to summarize, what one obtains in this situation is that one obtains exactly maybe what's been conjectured. One obtains that the algebraic wavefront set of spherical Arthur representations with parameter O check is equal to the Barbash-Vogin dual of that parameter. And in terms of this canonical unramified wavefront set, which I've introduced, you can actually say what that is exactly as well. They're the fibers of this map, of this element in ds bar. So this actually gives you some information about the p-adic wavefront set as well. So this is like it's an invariant which sits in between the p-adic and the algebraic one. So that almost concludes my presentation. I just want to say a couple of words about sort of this result and future future results. So so this paper was sort of a proof of concept paper to describe to illustrate how these methods can be used. But sort of current results, which I'm working on, generalize these results and calculations to a larger class of representations. So to hopefully forthcoming results will include bounds in the algebraic wavefront set for all Iwahoe spherical representations, and hopefully also in general to these unipotent representations of listic Propianic groups, which is sometimes also known as unramified representations. But yes, so that's my talk. Thank you.
Okay, yeah, thank you very much. So, and then questions or comments?
Can I ask a question?
Yes, sorry.
So can you go back to the slides where you just embed this reducible representation of wire group inside to a pair. The pair consists of a nilpotent orbit and a conjugacy class of the equivariant pi 1.
So do you mean the one about lifted generalized Gelfand-Grave representations, or?
Yes.
Yeah.
No, maybe next 2 page. I'm not sure yet.
Here?
No.
You mean the classification of unramified orbits?
Yes. No, this
yeah.
is DSGC. Yeah.
Yep.
So is this map given by the Springer correspondence?
No. So
this is the question is that so you have this DSGC, right? It looks very similar to this the one given by Springer correspondence, where you embed a representation of the wire group inside a pair, where the first component of the pair is also a nilpotent orbit, but the second component, instead of being a conjugacy class, you take a irreducible representation of this pi 1 GCO. Is there
exactly. Yeah, so that's a good question. So that's what just motivated this terminology, dual Springer parameters, and this difference that there's a conjugacy class instead of an irreducible representation.
Yes.
But the proof does not involve the Springer correspondence. It involves this classification in terms of the Bruhat-Tits building and results by Summers and McNinch, which parametrizes these objects in terms of certain triples of data on the complex reductive group. But the proof is very different. What is worth noting is the connection between the two is still open. So I mean, sort of there's the Springer correspondence does very naturally arise in a lot of these computations, and exactly the interplay between the Springer correspondence and these dual Springer parameters. I mean, sort of analysis has had to be done until now, but I guess there's perhaps more to be done to understand exactly how they interact. Yeah.
Okay, thanks.
Emile, could I ask on the same slide? In point 3, you say there's a canonical bijection, right? So when you say canonical, what do you mean? I mean, do you mean that it is the unique bijection satisfying some properties? Because this commutative diagram 19 does not uniquely characterize it, right?
Exactly, yeah. So I mean, canonical, perhaps I use the word canonical lightly. So there's also, so if you replace C, if you consider a reductive group defined over an arbitrary algebraically closed field, there is still a bijection, but the bijection is no longer canonical. So it depends on a choice of roots of unity of that algebraically closed field in correspondence to the roots of unity of C. But if you take the reductive group to be defined over C, this whole procedure which defines this isomorphism, there's no choice being made at any point, essentially, is what I mean by canonical sort of.
I see, but can you characterize what you have constructed by some property?
That's a good question. So I haven't thought about that. I wonder if you can. So
because, for example, you have for every fixed O, you have a canonical C, right? The trivial conjugacy class.
Yes,
so that would suggest that on the fibers on the right-hand side of 19, there's some canonical element in it, which seems unlikely. Yeah.
Oh, there is a canonical element. That's exactly right. So this is addressed in my paper. So this fits into a bigger commutative diagram, which I've chosen not to talk about in this talk. But if it corresponds, so if you take the hyperspecial points, the origin of your apartment, then the reductive quotient, like we saw in the case of SP4, it's the same group in the split case, but defined over FP. So that has the same root datum as the p-adic group. And when you're looking at geometric orbits, they only depend on the root datum. So if you lift that orbit from the reductive quotient upstairs, that is the thing that you get, which corresponds to the trivial conjugacy class.
Okay.
So there are a whole host of properties which this bijection satisfies, which I go into more detail into the paper. There are also, if you look at the conjugacy class, you can look at the order of an element in the conjugacy class, and then you can sort of look at the facet in which an orbit here comes from, and you can this bijection must preserve certain properties of the orders of these elements and things like this. So this bijection, it does satisfy a whole host of interesting properties.
All right. Could I trouble you to go back to like the very beginning? I mean, like maybe the first or second slide. Yeah. The reason is because you mentioned that, I mean, you define, I mean, your definition of unramified Arthur parameters, you sort of require it to be trivial on the Wavefront group, and I wonder if that's what you mean by it, because usually unramified just means, the parameter is trivial on the lean SL2 and also on the inertial group. So, but if you want it to be trivial on the whole thing, then I guess this is what people usually call the unipotent Arthur representations. So I wonder whether what you talk about, is it just for unipotent Arthur parameters or more general unramified ones?
So this section on automorphic forms, I've been told by my supervisor the motivation for this. So my knowledge of the automorphic form side of things is not particularly good.
No, but I guess what I was saying, so for the particular spherical Arthur representation you talk about trivial on Wavefront group.
So you cut out for me there for 1 second.
Oh, sorry. So for your theorem where you compute the wavefront set of the some representations, right? Those be such that their parameter is trivial on Wavefront group.
That's right. Yeah.
So in particular, it is a finite set of representations we are talking about, right?
Exactly. Okay. Yeah. So there's one for every nilpotent orbit.
Yeah. Okay. Thank you.
Yeah.
Okay. So any other questions?
I have a question about can you go back to the slide about this K orbit? I think already several people asked a question on that slide.
Okay.
Yeah. So this, this slide 4.3. Here I have a question. So do you need to assume that this group is split over the K, big K?
Yeah.
Or get this?
So in this talk, I've assumed split throughout. In the paper, this bijection holds if it's split over a maximal unramified extension.
Yeah, but if it's not split over maximal unramified, you will still get this map. But it's not an isomorphism, but maybe you will get an injection in some sense.
That's a good question. But I don't know enough about the non-split over an unramified extension case. So the ingredients for this proof is you need to be able to classify them by these reductive quotients. So
yeah.
can you define? So I guess the question is,
you still can have this reductive quotient, but it will not exhaust all the pseudo levies, I think. Maybe
okay. So in that case,
yeah. Anyway, this may be too much for the question. So I have another question about the canonicalness of this map. As you mentioned, you need to fix a hyperspatial point, but actually the hyperspatial points are not unique in general. You might have two choices.
Oh, you
I'm
might have
wondering,
two choices.
yeah, for example, for symplectic groups, I guess you will have two choices of the hyperspatial point.
So this one here as well.
Yeah. So anyway, you need to fix the hyperspatial to get the map.
Yeah. So this was something that I looked into as well, because usually when you talk about the Bruhat-Tits building, there's no origin in any of the apartments. Like, sort of invariant under the choice of chamber, the fundamental chamber isn't distinguished somehow. But the apartments are also defined for every split maximal torus, you get an apartment, and the definition, in some definitions of the Bruhat-Tits building, they do make a point of sort of distinguishing the origin somehow. So based on that, I've sort of, there's this canonical choice you can take if you take your apartments to have a base point. I don't know how unconventional that is in the general literature of Bruhat-Tits building. Maybe that's.
Okay, I see. Oh yeah. Okay, thank you very much for your explanation.
Thanks for the question.
Okay, could I ask two questions?
Yes, of course.
So the first is a follow-up with the Vtext question. So you're talking about the spherical Arthur parameter. So, but in your proof, you only use the Iwahara spherical representations. So the representation have the Iwahara.
Yes.
Yeah. So, but those kind of representation is more than just the unramified one. So how about this your approach to generalize to the other unipotent representations like the?
Yeah. So that's a very good question. So what you can do is these finite representations that you get. So if you're Iwahara spherical, the category of Iwahara spherical representations are, you can describe them in terms of the category of Hecke algebras with respect to the Iwahara subgroup, and then the restriction to these finite representations are restrictions to sort of parahoric sub-algebras of the Iwahara Hecke algebra. And Lustig has given a description of multiplicities of irreducible modules of the Iwahara sorry, I keep on saying Spherical algebras, Iwahara Hecke algebras of the finite groups of Lie type in terms of certain character sheaves. So the hopes is that analyzing the character sheaves which occur in this manner, so far the intermediate results which I've obtained for future work is that an inequality in this direction will hold in general for Iwahara spherical representations simply by general theory of unipotent support of character sheaves. So you get that one almost for free, actually.
So this for the second one, the K bar, the stable nilpotent orbit, this equation is hold for the, you expect to hold for all the, I mean, your method can work for all the unipotent representations as the.
That's the hope, yes.
Okay.
So I've only
That's
done
great.
computations for the Iwahara spherical ones, but the hope is that the methods will apply to, in general, representations with unipotent reduction. So
Okay.
that's the direction for future work, essentially, to generalize these methods.
Okay, thank you. And also, just to follow the judges, could you clarify the group G is split over the bigger K, but not necessarily split over the little k, right? It could be like
yeah.
Okay, non-split, non-causative split over the little k.
Yeah. So for this bijection, that's correct. Yeah.
Okay.
Yeah. For the results about wavefront sets, we do need that only holds for split groups.
But for your result, I mean, the result for your wavefront set case, do you need a assumption your original G defined over the you no need for the split over little k, right?
So the general theory that I described holds over, not split over little k. It's just for the explicit computations which I do with the spherical Arthur representations, where I use like actual parametrizations, where I require a split. So you're right. So all the general theory should hold more generally.
Okay.
And, yeah.
Okay. Just one more question. In the last slides, your main theorems about the bigger K, the unramified nilpotent orbit, you have the inverse map, the D inverse with the DAO check, if I remember correctly. Okay, so this D inverse is going to cover all the fibers of the stable orbit or just a partial of them?
It will.
Say, for example, if I have a K-bar orbit, and when you're talking about it, you have the previous map is coming, you also can split the, sorry, you're going to become like several unramified orbits. So those several orbits going to all support for the WF pi or just some of them? So
only a few of them. So not all of them will be covered. So this is genuinely a finer invariant than the algebraic one. So this actually tells you information about the p-adic orbit which arises.
I see. How about the little k orbit?
Yeah. So, yeah.
How about the little k rational nilpotent orbit? You have this is unramified orbit, but you also could have like the little k. You're gonna split more rational orbits there, right?
Exactly. Yeah. So this will only tell you.
Yeah.
So we don't. So exactly. So somehow in the p-adic case, the p-adic wavefront set is too fine and invariant to get a proper handle on, and the algebraic wavefront set is sort of quite coarse. But somehow I think what I've found sort of in my research is that the unramified one is sort of the sweet middle ground, which has the most nice geometric description in terms of the dual group, and it does give you information about the p-adic orbits, because the p-adic orbits have to lie inside of these unramified orbits.
I see.
But yeah, but you can't.
But do you think that the
Sorry.
But do you think that passing from big K to small k could be reduced to a problem over finite fields? I mean, you have an analogous problem with finite fields.
Yes, I think it could be, but it depends on certain conjectures which haven't been proved. So this conjecture that all of the wavefront set p-adic orbits lie in the same geometric orbit, then it will just reduce to a reduction to doing the finite field problem. But without a proof of that, it becomes more delicate to be able to completely reduce it. But I have some ideas on maybe there is a chance, but it's unexplored as of yet, and I'm not entirely. I wouldn't want to say anything too specific about it because I really don't have any specific conjectures. But yeah, you're exactly right. I think it will boil down to that.
Okay. Thank you very much. Okay. So, any other questions? Okay. If you have no question, thanks, Emile's beautiful talk.
Thank you.
Okay, thank you very much. I'm gonna just end the recording part.